I'm starting the recording right now, so we're starting right away. So we're going to start today's class by solving this problem. We're going to see about this and try to get the things around here. A signal is to be transmitted along a cable system of total length 125 kilometer. The cable has an attenuation of 7 decibel per kilometer. Amplifiers, each having a gain of 43 decibel. Is the voice all right? Can everybody hear me right?
Yes, sir.
Achha,
Yes,
okay.
sir.
Okay, thank you. So the cable has an attenuation of 7 decibel per kilometer. Amplifiers, each having a gain of 43 decibel, are placed at 6 kilometer intervals along the cable as illustrated in figure 12.1. State what is meant by the attenuation of a signal. Now, the important part that I'd like you to understand that the cable has an attenuation of 7 decibel per kilometer. And we are placing these amplifier stations 6 kilometers apart, which means within this 6 kilometer traveling, the total drop of signal strength would be 42 decibel. 6 kilometer into 7 decibel per kilometer multiply. So from here to here, or from here to here, from one station to another station, the drop of signal strength is going to be 42 decibel. And we are attaching these repeater stations amplifiers, each of which has a gain of 43 decibel. So basically we are overcoming the loss by 1 decibel extra, which is good. We could give exactly 42, that would be also all right, but we are just adding 1 decibel more because they prefer it, so no big deal. The question says, state what is meant by the attenuation of a signal. So you just write this up. This calculate the total attenuation caused by the transmission of a signal along the cable. Total attenuation would be total distance multiplied by the 7, so 125 kilometer into 7, that's whatever you get. Simple multiplication, but they have given a large space. I don't know why, maybe to confuse your kids, but it's just a simple multiplication. You get the total attenuation. How much is this gonna be? 125 into 7 gives you how much? 875, I think. $125 into 7 gives you how much? My calculator, if I see. $125 into 7. Polaban, can 125 into 7 kortesi? Ei logicta jodi na bujho, then you ask me. But if you are good, then we'll move on. If you have questions, please feel free to share.
Total attenuation bear corrigible, sir.
Yes. So I have the participant list and the chat window here as well, so that I can see if you raised your hand. That will help. So the next question that we have, where it says that the total signal gain as a result of the amplification by all of the amplifiers along the cable. Now, this is the important bit. The total signal gain as a result of amplification by all the amplifiers along the cable. The first thing you have to judge, you can pretty well see that the number of each amplifier gives us a gain of 43 decibel. But the question is, how many amplifiers are we gonna have? That's the part that you really need to understand. Now, to make sense of this information, let me just show you a figure so that you can make better understanding. So let's say, let me use a thicker. Let's say this is a sending station. So from the sending station, we're sending the signal. After 6 kilometer, we're placing one amplifier station. So that's our amplifier station 1, which is covering the previous 6 kilometer. Then we have another one, which is covering the previous 6 kilometer. So each amplifier station is responsible for the previous 6 kilometer. It is compensating for the signal loss in the previous 6 kilometer of length. So you go on like this, and because these are all 6 kilometer each, so if you get the closest multiple of 125, it can be either 120 or it can be 126. I've written the two multiples of 6. So if you consider that this is the amplifier which is placed after from here, let's say this is 125 kilometers. Sorry, not 125. Let's say this is 120 kilometers. So this is our certain number of amplifier. We're gonna find that out, but bear with me. If this amplifier is behind this amplifier, we have a length of communication channel that is 120 kilometers, which means after this we have how much? We have only 5 kilometers left. Are we going to need another amplifier station over here, or are we going to have the receiver station over here? What are we going to have? We're going to have a receiver station over here. So we're not going to need another amplifier over here. So practically speaking, Using the amplifiers that we have over here, we're gonna cover a total length of amplification that is relevant for 120 kilometers, not 126. Now you might wonder, why is this judgment necessary? Why am I even blabbering about this? What's the importance of this information? Because it is that judgment of that 120 kilometer that can give you the exact number of amplifier station you're gonna have within this communication channel. Each 6 kilometer is covered by one amplifier station. So if you just divide 120 kilometer by 6, you get 20 stations. So essentially you're gonna have a total of 20 repeater stations within this channel, not 21. Now, if these people asked us that if, let's say, if this number was, let's say, if this distance was not 125 kilometer, let's say if distance was, let's say, 131 kilometers. If this was 131 kilometers, then what would have happened? Then you have to once again get the two numbers which are the 6 multiples before and after that. What is the earlier 6 multiple of this number and what is the latest 6 multiple of this number? Someone give me. 131 divided by 6. How much do you get? 21.
1.8.
1.6 gives you 126. So the earlier one is 126. The later one is 132. So in this case, once again, the repeater stations would be, so if the total distance is 131 kilometers, so this falls within the halfway of these 2 points, which means you have to cover from 126 backwards. So you have to cover a total of 126 kilometers, not 125 kilometers. So if you divide 126 by 6, you get 21 stations. The point that I'm trying to make in here is that if you divide the total length by the gap size, whatever the smaller number you get, that you will be relevant for your number of repeater stations, because it is pretty important, because if you don't get that number correct, you'll get this answer wrong. Have a look at this question. The question says that the total signal gain as a result of amplification by all the amplifiers along the cable. So you have to know precisely how many amplifiers are you using. In this case, to cover a total of 120 kilometers of length, we are going to use 20 amplifiers, and then the rest of the 5 kilometers, we don't need any more amplifier because it is less than 6. So we have 20 amplifiers, so 20 multiplied by 43 gives you the value. If we have a look at the mark scheme, this is question number 19. So let's jump into question number 19. There it is. It says that 20 amplifiers gain equals to 20 into 43. So they have just given the correct answer. In the mark scheme, it says that B1 was generally correct. B2, there was considerable confusion here, with many candidates assuming that 21 amplifiers would be used, thus giving a gain of 903 decibel. So this was the wrong information. General considerable confusion. So I don't want you guys to have this confusion. এই ডিসিশনটা কি বুঝে গেছে সবার যে কেন এখানে এটা 20 হইলো? Any confusion so far? Anyone? No. Okay. So
এখানে কি আমাদের সিগন্যালের যে স্ট্রেংথটা ম্যাটার করবে যেটা আউটপুট সিগন্যালে যাবে?
Well, that comes in the later part. যে এখানে আসতেছে. We're gonna see about that right here. So let me just place this information, and beyond this, I'm gonna pick up the other part. So here, just a second, Bolaban, এক minute, আসতেছে আমি. So if we calculate the total gain of the whole system, this is gonna be 20 multiplied by 43. That gives you how much? $860. ভুল লিখতেছি?
No, sir.
860 decibel. That's the gain that we're gonna have. Then the question says the input signal has a power of 450 milliwatt. Use your answers in B to calculate the output power of the signal as it leaves the cable system. As it leaves the cable system basically means as it is received on the receiving end. So that means we are basically trying to find out the output. So you can see over here, the total loss signal is 875, total gain is 860. So if you do the subtraction, you're gonna have a 15 decibel of reduction. So you're gonna basically have attenuation, you're not gonna have gain. So if we do this part over here, we can go for attenuation. The basic formula, attenuation equals to 10 log P in by P out decibel. So here the attenuation is gonna be subtraction, that is 15 decibel. So 15 equals to 10 log. The final answer has to be also in 4 milliwatts. So I'm only writing 450 over here, not writing the 10s power. We don't need that. By P out. এখান থেকে ক্যালকুলেট করে বের করো যে P out কত হয়। Help yourself. 10 to the power 1.5. 10 to the power 1.5 equals to এত 450 হবে answer. 14.2. দেখো তো এটা আসছে কিনা। I hope I'm not wrong. Yeah, 14 milliwatt works. So you can see over here that they have used the overall gain as minus 15 decibel or attenuation of 15 decibel. I would prefer this one, attenuation of 15 decibel. And in the equation they've used minus, and then you use the output power on the top and input power at the bottom. I preferably don't like this format of equation. Don't bother to learn in the negative form. Learn exactly what I told you, because that gives you less thing to remember. That you are having a signal power drop, so attenuation equals to 10 log P in by P out. That basically helps to structure the formula in a much more simpler version. If you can, or if you find this logical and easier to remember, you can always remember this, no big deal. But I personally don't recommend this for the sake of ease of learning. So that's one question that I wanted to solve. And the other question that I would like to go for, that's it for that question. The other question that I'm personally interested is this one. Yeah, we have to draw this one. And then there should be another question about the frequency modulation. Frequency modulation question জানি কোথায় আছে। আচ্ছা আর এটা দেখাবো, এটা পর আরেকটা কোশ্চেন দেখাবো। Let's pick that up and place it here. Okay. So let's have a look at the content of this question. Have a look. Figure 10.1 shows the variation of frequency P of the power of a radio signal. So we have only 3 spikes, which means the information signal was a single frequency information signal. There was no quality in this because we only have 3 spikes. This is the carrier wave frequency. This is what called the sidebands, and the whole difference is bandwidth. Half difference is the maximum signal frequency component of the information signal, which in this case is only 1, because there is no maximum, because there is only 1 frequency, because we have 3 spikes. Say the name of the type of the modulation of the radio signal, amplitude modulation. The component of the frequency 50 kilohertz is called the carrier signal. The components of the frequency 45 kilohertz and 50 kilohertz, these are called side bands. Student অনেক সময় এই জিনিসটা ভুল করে। The mistake that you should not do that, do not write this as to be bandwidth. The bandwidth is the difference of these two values. These values themselves are precisely called the sidebands. So you have to write the word sidebands over here, not bandwidth. So the bandwidth of the radio signal, that is the difference of these two, that is 10 kilohertz. So you write this thing 10, and that's it. And then comes this question. This is the part that I wanted to show you. On the axis of figure 10.2, sketch a graph to show the variation with time t of the signal voltage of figure 10.1. So this is the question that we are trying to solve right now. We have to represent the modulated signal that where this was obtained, from which this was obtained, in this graph. So what are we trying to draw here? We are precisely trying to draw a graph that looks like this. We are trying to draw a graph that looks like this. We're going to try to draw this graph, but with the appropriate scale. One example that I would like to show you, or one example that I could show you that, আচ্ছা ওই কোশ্চেনটা পরে যাচ্ছি। সো এই গ্রাফটা আমরা কিভাবে প্রপারলি লিখতে পারবো? So let's have a look over here. Let me help you. The carrier frequency is 50 kilohertz. Try to understand. 50 kilohertz means, because in this case for this graph is horizontal axis is given in microseconds. So let's find out what is the time period of the carrier frequency. So carrier frequency is 50 kilohertz. So in terms of microsecond, what will be the time period? 1 by 50,000. 1 by 50.
20 to the power minus 5.
Yes, this is late. So in terms of microsecond, how many microseconds is gonna be? If you give engineering, you're gonna get 20 microsecond. So we get 20 microsecond. That's the time period of the of the carrier signal. Now, what is important? This will be the cycle life of a single wave. One completed wave will be completed in 20 microseconds, which means between this much space we should have one crest and one trough. Between these two space we should have one crest and one trough. So they have given us a convenient shape over here, which is good. Then we have to find out the how often is gonna go rise up and go rise down. So we have to go for the signal frequency. Here you can see that the bandwidth that we found was 10 kilohertz. So because the bandwidth was 10 kilohertz, so I can write that the frequency of the signal information that would be 5 kilohertz. So 5 kilohertz would basically mean that time period of this signal would be 200 microsecond. 200 microsecond. 200 microsecond means what? Time period being 200 microsecond essentially means if I have the information signal that somewhat looks like this, from one crest to another crest, the gap should be 200 microsecond. Or from one trough to the next trough, I didn't draw it, let's say I draw it now. This should be 200 microseconds. So between two similar amplitude of the amplitude modulated signal, the space, the time amount should be 200 microsecond. That's the information. You have to first figure out these two values. Without these two values, you cannot draw this. Now, then comes the easier part, that on the y-axis we don't have any scale, so we are not we don't have to essentially show this by an appropriate value, but we have to keep the proportions proper. Mugdha, are you saying something in the channel? No, okay, never mind. So we have to keep the proportion same. What do I mean by the keeping the proportion same? Let's say I'm going to show, let's say I'm gonna start with the crest. If I want to start with the crest, so let's say if I just show you this graph, where is this graph? Let's say if this is the graph. Let's say I want to represent in this figure precisely this. Where is the annonate? Can I get rectangle here? Shapes. Do we have shapes? Format. Line width, font, B, stamp, arrows, teaching, no text, select, mouse. No, I don't. Acha, I mean normally that hey. Let's say I'm gonna have draw rectangle. Okay, so let's say I want to draw this much space of the graph over here. If you wonder why this much space, because if I start from the crest of the graph, it would be easier for me to finish the graph at a crest. So I would know precisely how much I have to cover, because if you have a good look at the given question, where is the question? Here's the question. You can see that over here we have a total amount of time that is represented with 220 microsecond. That is slightly bigger than 200 microsecond, which means we should be able to represent one full cycle over here, either from a crest to crest or from a trough to trough. So either of them can work, but I just want to start with the crest because that's just my preference. So clear all drawings. Okay, this is gone. So what I'm gonna do, using my ruler, and you can try this with your worksheet, in your worksheet as well. Using a ruler, try to specify two levels over here. That one level that you're going to represent for the maximum. Let's say I'm going to use this much as my maximum level, and let's say I'm going to use this much as my minimum level. And the same thing, do the same thing on the opposite side, maximum and minimum. The minimum doesn't have to be exactly at the middle, but these two dots should be symmetric to each other. So the way I'm gonna do is each of the cycle is gonna go up. So the first wave that I'm gonna draw, which is a bit thinner, maybe use blue. So the first wave that I'm gonna draw is gonna go up like that, reaching up to the peak over here. And then I'm only drawing this much just to show you some example. Then it should drop down to minimum amplitude at half of the time period, which means because I'm starting from 0, right, around 100, so about a position আমার যে crest আসবে, a carrier wave, the crest of the carrier wave, that should align up with the lowest amplitude. So there should be a gradual decrease over here, and then there should be a gradual increase all the way up to the 200, which means the cycle that I'm going to draw at 200 is going to be as tall as the first cycle. So this is going to be a pretty tall cycle. So right up over here. So halfway around here. So let's say right up over here. So this is going to be a large cycle as well. So there's going to be a gradual depression over here, something that I tried to show you right over here. So you can see there's a gradual depression. What should be the shape of this depression is not very important, but showing the gradual decrease is pretty important. So what you can do, or what I do recommend, that draw a very light line, draw a very light line to draw up a shape like this, not a straight line. Actually, not a straight line. Draw with your pencil, draw a curved line like this, and then draw a line like that. It doesn't have to be perfect, doesn't have to be beautiful. It just have to give you a small bit of understanding, and achieve the same structure over here as well. Let's say you're gonna have the cycle going all the way down over here, and this is gonna be your cycle meaning up over here. So from here you also try to achieve the lowest part. So this is gonna be, let's say this is gonna be my lowest amplitude over here. So try to draw up this part somewhat like this. So draw these two lines quite thin, because you eventually have to erase it up. Beyond this point, what you can do, you can draw your actual curve with a hard pencil, or with a bit more pressure, so that later you can just rub your pencil over this line to get rid of this reference line. Or that's one thing you can do. Or the other thing that you can do, you take up your ruler and hold your ruler, ruler or set square, anything can work. Take up your ruler. I think a ruler would be good. So let's say take up your ruler and move your ruler like this. So, and give dots in every single position that you're gonna make the graph to go in. So let's say this from 0 to 20 is one cycle, and then from 20 to 40 is another cycle. So here we're gonna have one crest. So you're gonna give one dot right here for that peak, and then if you move it halfway over here, you're gonna give one dot over here. It doesn't have to be very perfect, but this can help you draw the graph with significant accuracy, because this is a 3 marks in it. So it's pretty much doable within 3 minutes of time if you know how to do this. So give all of this top and up and down dots, and continue within your graph all the way up to the last. That way you will have all the reference dots, and then you can erase this reference line, and then you can start freehand drawing for the whole curve. This curve, which is going to be a final answer, doesn't have to be beautiful. I'm telling you once again, it has to be well representing, which means there has to be a significant, there has to be a proper showing of gradual decrease of these amplitudes, and then up to the half of the time period, which is 100 milliseconds, and then there should be gradual increase of this whole thing. So if that part makes sense to most of us, I'm going to try to complete this graph as best as I can. So if you have any question, you can ask me.
Sir, do we have to do the same thing but with a frequency modulated graph?
No, you will never be asked to draw a frequency modulation graph, because a frequency modulation graph is practically pretty difficult to draw. I have not seen a single example where a frequency modulated graph was asked to be drawn, because drawing that thing can prove to be really difficult for a manual drawing process. It's very easy to do the compression and the expansion in a computer environment. You can just select a part and squash and expand it, but for freehand drawing graph, frequency modulation is very difficult. They never ask you about drawing about frequency modulation, because frequency modulation is not altogether discussed in detail for your syllabus. But there is a single math that usually comes every once in a while, which I'm going to show you after this problem.
Sir, Fahim in the chat box is asking where the 5 kilohertz came from.
Oh, I got the 5 kilohertz by halving the bandwidth. The bandwidth over here was 10 kilohertz, 45 through 55. So if you do the half of that, because the bandwidth is 2 FA, so that is 5 kilohertz. Fine, bucho.
Yes, sir.
Okay. So এই হচ্ছে গ্রাফের shape. I'll give you some time for all of you to draw this graph on your worksheets. I'll give you, let's say, 2-3 minutes because I want you to complete this on your own right now. So take up your pencils, light pencils, soft pencils, and do this. This graph doesn't have to be beautiful. It has to be properly representing. So this and at the end, this soft line should not be there, because the reason it's important that you do not have this reference line is because when the modulation will happen, you will never get this line. So if you keep this line in your graph, the examiner might misinterpret over your idea that you might think that this kind of a line should also come in the modulation, but that's not true. So it's important that you don't keep this reference line that you use to draw the whole graph. So make sure to rub it off before you actually finally submit your copy. So complete this. I'll give you 2 minutes, everyone. And I'll pause the recording. So we're resuming the recording. So we'll now start solving this question number 32. So this is a question that is this: the variation with time of signal transmitted from an aerial is shown in figure 11.1. So we have this signal. So let's pick up this signal and try to place it onto the next column space that we have right up here. So that's the graph that we have, and then the question comes in right here. This is just a reverse version, like I said, of the earlier question that we saw. So should not be very difficult, but you have to watch carefully. So we have the whole thing over here. This is a inverted graph. So whenever you'll have your question paper, you can basically turn your question by 90 degrees so that you can easily see this thing. Because I can also do this thing in my case, I'm gonna select this whole thing up and cut it off. And I hope I'll be able to rotate this. Don't get caught. Which means I have to select a very large portion of this thing and then rotate this and select transform selection. Okay. So I rotated my graphs for easier viewing. So I'm gonna see it from this perspective. And you can rotate your own original copy physically so that you can see it easily as well. So let's have a look at this graph. You can see that this graph essentially shows us the variation of the information signal. The first thing you have to find out is what is the signal frequency. The signal frequency, because this is the question that you have to solve. That state the name of this type of modulation transmission. This is amplitude modulation. So you have to write this whole name, amplitude modulation. Don't write short form, preferably. Then the question says use figure 11.1 to determine the frequency of the carrier wave, and then the information signal. And on the axis of figure 11.2, draw the frequency spectrum. So we have to draw the frequency spectrum over here, which got cut off. I should do this now. Paste. Transform selection path. And we have the whole thing over here. Okay. Replace the whole question. I have to bad. So this is the question. So we have to find out the frequency of the information of the carrier signal. So let's have a look at. Let's find out the time period. You can see it very well that it goes. This was the crest of the. This is the. I mean, the 1 cycle of the carrier signal is this much long. So that's basically 10 microsecond. So the time period for the carrier signal equals to 10 microsecond. So convert that into frequency. Frequency of the carrier কত হবে? 1/10 into 10 to the power minus 6. এটা হার্জে কনভার্ট করে দেখো কত আসে। কত আসে দেখো।
10 to the power 5 hertz.
100 kilohertz আসে আমার, or 10 to the power 5. Yes, 10 to the power 5. So this gives you 10 to the power 5. So এখানে জাস্ট আমরা 10 to the power 5 লিখে দিলাম। বাট তোমাকে এখানে অবশ্যই এখানে তোমার ক্যালকুলেশনটা দেখাইতে হবে যে তুমি কিভাবে ক্যালকুলেশনটা করছো। So 1 divided by 10 microsecond এই ক্যালকুলেশনটা এখানে দেখাইতে হবে। Then comes the information signal. Information signal time period বের করার জন্য we are simply going to judge the graph from crest to crest or trough to trough. I like crest to crest. So let's say from here through here. So here to here judge করার থেকে 0 থেকে 100 judge করাটা easier because that's the start point in the start point. So we don't have to bother about the halfway crossing of this whole thing. So 100 microsecond is the time period for the information signal. So for the time period for the signal is 100 microsecond. So because this is just 10 times big, so I understand that the actual answer would be 10 times smaller. So this would be 10 to the power 4 hertz, I believe. ঠিক না? I think so. টেন টু দ্য 4 হবে না? দেখো তো এটা কত হয়? 10 to the 4 হয় না? 100 to the power 6, হ্যাঁ 10 to the 4 হয়। So the information signal frequency হচ্ছে 10 to the power 4 hertz. আচ্ছা, এরপর আমাদেরকে এখানে একটা বলছে হচ্ছে on the axis of element to draw the frequency spectrum, the variation frequency on the signal voltage of the signal from the aerial, mark relevant values on the frequency axis. So this is basically that drawing the carrier signal and the other two parts. So this is 10 to the power 5. You can draw this in your basic format. I'll preferably convert this into kilohertz. So I'm going to write over here frequency slash kilohertz. That's the first thing that I'm going to do. So the carrier signal is going to be at 100 kilohertz. So I'm going to write 100 over here. And the once another sideband would be 100 plus 10. The other one would be 100 minus 10. So this would be 110 kilohertz. This would be 190 kilohertz. So that's how I would preferably write. But if you only want to write in hertz, you better write the whole number. So this will be 100,000. This will be 110,000, and this would be what? 99,000. No, 9,900. No. 9 এরপর চারটা শূন্য। বলবান এটা কি বুঝছো সবাই? এখানে কি করছি?
জি স্যার, প্লাস মাইনাস করলাম information.
Exactly, basic plus minus, and তারপর হচ্ছে bandwidth of the signal. Bandwidth of the signal হচ্ছে 20 kilohertz. So you can write 20 kilo, or you can write 20 into 10 to the power 3. That also works. So this is just a reverse of this original of the earlier question that we just did. So এখানে আমাদের basic signal দেওয়া আছে, signal থেকে আমাদেরকে frequency signal voltage versus frequency রাখতে হয়েছে. So that's pretty much that thing. I'd like to verify the answers that I did from the mark scheme because I'm a bit skeptic about this. Number 32. Let's jump over here. 32 is right there. 100 kilohertz, 20 kilohertz, 100 kilohertz, 90 kilohertz, and 110 kilohertz. Lines at 90 kilohertz, 100 kilohertz, the same length after shorter than 100 kilohertz. Bandwidth 20 kilohertz. Full marks. Beautiful. One thing you should know that the unit of a certain quantity in a graph always shows up with the variable. So preferably write the unit over here. Don't individually write the frequencies over here. That's not essentially a crime, but that's a wrong way to represent the graph. You should know this by now. Just I'm reminding you to help you understand. So that's one question that I wanted to do. Any question about this question? Any confusion? Anyone? No. If you have a question, let's
do we have question number 29 in our syllabus of this worksheet?
29. I'll have a look. No, 29 is bad. Everything that is about PST network is bad.
Okay, sir.
Achha. The other question that I wanted to do was, I think 24. Yeah, this is the one. This is the one question that we have about frequency modulation. This is just some calculation. I'm going to help you understand this calculation from this part. So let's get rid of everything. Blank slate. Okay. Have a look at this. Describe what is meant by frequency modulation. So in this question, you write the definition of frequency modulation. So if you try to write it in your own words, if I try to write it in my own words, I'm going to write that it is the combination of an information signal with a high frequency carrier signal in which the frequency of the carrier signal is varied in conjunction or corresponding to the amplitude variation of the information signal. Amplitude variation, no, displacement of the information signal, sorry. The frequency of the carrier signal is varied in conjunction with or corresponding to the displacement of the information signal. That's supposed to be the correct definition. I'll have a look. You can in your mark schemes as well, or you can bear with me to see it from here. Number 24, it says Frequency of the carrier waves in synchrony with the displacement of the information signal. Exactly. Frequency of the carrier varies in synchrony with the displacement of the information signal. Generally, the answers to this part of the question were good. So, Purabanda definition bhalo likhche. Then comes the mathematical part. Have a look. A sinusoidal carrier wave of frequency 600 Hz and an amplitude of 5 volt. খেয়াল করো কি বলতেছে sinusoidal carrier wave has a frequency of 600 kilohertz and an amplitude of 5 volt. So this is a property of the carrier wave. The carrier wave is frequency modulated by a sinusoidal wave of frequency 7 kilohertz and amplitude 2 volts. So this is basically our information signal. This is by which the modulation was done. So this is our information signal and this is our carrier signal. So this is carrier, this is information. The frequency deviation of the carrier wave is 20 kilohertz per volt. This is the part that is important, which I told you in the first class that there is a method to this madness for how this variation is done with space. So this is the important information. Have a look. The frequency deviation of the carrier wave is 20 kilohertz per volt, which means for every volt variation of the information signal, the carrier wave is going to have a frequency variation of 20 kilohertz. That's what this 20 kilohertz per volt. So each volt of the information signal will cause the amplitude, will cause the frequency of the information of the carrier signal. Frequency of the carrier signal vary by 20 kilohertz. So the question says, determine for the modulated carrier wave the amplitude. Carrier wave amplitude perfectly same thakbe because this is frequency modulation. The amplitude will not undergo any change. So this is going to be perfectly 5 volts. So you can write 5.0, you score 1 mark. What will be the maximum frequency? Maximum frequency will be what the frequency that you are going to have added corresponding to 2 volt of amplitude of the information signal. So 2 volt gives you how much kilohertz variation? 2 volts gives you 2 into 20 kilohertz. That is 40 kilohertz, which means the maximum frequency is going to be 600 plus 40. I could write this over here, but essentially you don't have to write this because there's no space because they don't expect you to do any working over here. So that is 2 into 20 kilohertz. That's the amount of variation you're going to have. That is going to be 40 kilohertz variation. So maximum frequency is going to be this much plus 600. Minimum is going to be this minus 40 kilohertz. So this is going to be 640 kilohertz. And over here we're going to have 560 kilohertz. এই ক্যালকুলেশন দুটো বুঝছো কিনা দেখো। This is about how much maximum reduction and maximum increase of the frequency of the modulated signal is going to be because of the amplitude of the information signal, because it is the amplitude at the where you can have the maximum compression or maximum dilation. So that's how it works. This much is pretty simple. And then the number 4 says the number of times. এই কোশ্চেনটা ওয়ার্ডিংটা খুব ইম্পর্টেন্ট, ওয়ার্ডিংটা ভালো করে খেয়াল করো। The number of times per second, that the frequency changes from maximum to minimum and then back to maximum. The number of times per second that the frequency changes from maximum to minimum and then back to maximum, which means they are asking us that, let me show you. Have a look at this graph. This is the frequency modulated graph. What you can see over here, that in this graph, here we started a certain wave. This, let's say over here, the frequency is the same as the carrier wave. Then we had a compression increasing. So we have the maximum frequency right around here. And then we have decrease of the frequency, and we have the minimum frequency somewhere around here. And then we have increasing once again, and then we have the maximum over here. So this is one of your maximum point. This is one of your maximum point. The question is asking you that how many times per second will the modulated signal will experience this maximum to maximum? How many of these maximum frequencies is there gonna be within a signal of 1 second? এক সেকেন্ডে যতটুকু মডুলেটেড সিগন্যাল বের হবে ওই এক সেকেন্ডের সিগন্যালের মধ্যে এই কম্প্রেসড ফ্রিকোয়েন্সি কয়টা থাকবে? So you have to understand that each of these higher frequencies is basically the result of one of those crests. So how many crests do you have in the information signal in 1 second? That is basically the frequency of the information signal, and the frequency of the information signal is how much? 7 kilohertz. Have a look. Frequency of the information signal is 7 kilohertz, which means you're gonna have 7,000 crests in that signal of 1 second or 1 second long signal, and you're gonna have 7,000 troughs in 1 second long signal. This question is basically the same thing. The number of times per second that the frequency changes from maximum to minimum and then back to maximum. So maximum থেকে minimum থেকে হয়ে আবার minimum থেকে maximum হবে, এই চেঞ্জ টুকু 1 সেকেন্ডে মোট কয়বার হবে? That's basically asking how many cycles of the information signal is gonna be per second. So the answer to this question is 7,000. বুঝা গেছে কিনা বলো? If you have question, ask me right now.
So basically, same as the frequency of the information signal, right, sir?
That's what they are. That's what you have to understand from this wording. If they asked us that the number of times per second that the frequency changes from maximum to minimum, if they only asked us this much, that would also be 7,000. Maximum থেকে minimum dropটা হচ্ছে কয়বার? I mean, if you only consider maximum to minimum, if you only consider this much change, how many times does this change per second? This also happens 7,000 times. You have to understand. Here to here,
That's one wavelength.
not just half of a wavelength, but a very specified half of a wavelength. How many times does the signal changes from maximum to minimum? So we're not dealing with from minimum to maximum, so we are just not carrying it. But how many times will this drop from maximum frequency to minimum frequency will happen? Or how many times will this change happen? So this change happens once, and then we don't have to count this one, and then once again we're gonna have this one. So we're basically skipping half of the part of the graph, but once again that change will also happen 7,000 times. How many times the signal drops from maximum to minimum? 7,000 times. How many times does the signal increases from minimum to maximum? 7,000 times. How many times does the signal changes from maximum to minimum and then back to maximum? That's basically one full cycle. That is also 7,000 times. বুঝা গেছে কি?
G, sir.
Everyone else, please respond. এটা কেন 7,000 হয়েছে এই জিনিসটা বুঝা গেছে কিনা? So that's basically the single question that we have in this entire worksheet for about frequency modulation. Sometimes they do give us this kind of question. Most of the cases they give all of this information: the carrier wave, the information about the carrier wave, the information about the information signal, and also the frequency deviation is also given, and you just have to do this set of calculation. This type of questions are actually very rare, like super rare. When I first came across this question about frequency modulation, I was to be honest really irritated, because the syllabus doesn't have any type of this question, but they gave these information. Then I went into Google and find out what this frequency deviation thing means, and then I understood that this is basically the scale by which the whole modulation or frequency modulation is done. Then I could solve this question and eventually transfer that idea to the students. But this is a very simple question. In my opinion, it's a pretty simple one, but if you don't know the know-how for how to deal with this information, you would be in a big trouble. That's why I wanted to show this question. So that's pretty much it from my end, that the questions that I personally wanted to discuss from this worksheet. If you have anything else that you have attempted but you couldn't solve, or the answers didn't match, the mark scheme seems a bit goofy, exam report seems a bit troubled, this is a time that you can ask me. So shoot your problems in the chat box. I'll take one by one, or from any other worksheet that for that matters. And you can also ask me questions from the other questions which are not included in this worksheet, or from other sources. If you have attended some questions in your classwork for your school, or if you are going for a secondary fees coaching where you came across some problem but you would like to have the explanation from me, all are welcome here. Problem solving is open for every source without prejudice. Anyone?
Sir, I had a problem in capacitance.
Capacitance worksheet বের করব?
না স্যার, মানে কোয়েশ্চেন পেপার করার সময় পেয়েছিলাম আর কি।
তাহলে ইয়ার বলো, আমি কোশ্চেনটা বের করি।
স্যার 41 May June 18।
May June 1841. Beautiful. Muthu, thank you. We'll go for that. It's to Lacko ekhane. Chat box to Lacko so that if anyone who couldn't hear, they can actually look it up. Tutoring material. May June 18. So usually SAT. 41. This one?
No, sir. Number 7, I guess.
Oh, got it.
Sir, 7, B2 and C. I didn't understand that part.
Achha, let's have a look. Let's remember the capacitance of parallel plate capacitor. That's the definition. You fill this up. A parallel plate capacitor C is connected to the circuit as 24/7.1. So we have a two-way switch. We have a 120 volt DC supply capacitor. So closing into the X will charge up the capacitor in minimum time because there is no resistance in the circuit apparently. And then closing it to the Y part is gonna drain the capacitor in minimum possible time because once again apparently there is no resistance in the circuit if we consider the ammeter to be ideal, but it shouldn't be. When the switch is positioned, the battery of filter memory force 120 volt negligible internal resistance is connected to capacitor C. When the switch is positioned, the capacitor is distributed through the sensitive ammeter. Okay. The switch vibrates so that it is in first position X, then moves to position Y, and then back to position X 50 times each second. Okay. The current recorded in the ammeter is 4.5 microampere. This is the important bit. So the current recorded in the ammeter is 4.5 microampere. Determine the charge in coulomb passing through the ammeter in 1 second. That's pretty much easily doable. You just multiply this whole thing so you get the value. You have to understand one thing, that whenever they say that the ammeter recorded in this through this sensitive ammeter is 4.5 microampere, this essentially implies that the question tells us that this cell or source is negligible resistance. So there is no resistance in this circuit whatsoever, which means theoretically it will take 0 seconds for this capacitor to be charged from 0 to 120 volt. It will immediately go to that voltage value. And then whenever it will be connected over here, that 120 volt would be drained through this ammeter circuit while the current would be recorded as 4.5 microampere. Now, okay, acha. I mean, further question. Then the question is the charge on one plate of the capacitor each time it is charged. The charge on one plate of the capacitor each time that it is charged. Okay. Q equals to CV দিয়ে আমরা এখানে QCV বের করতে পারবো না. We calculated the charge. It is put back and through. This is this uncertainty by 50. I think.
Sir, why?
The switch vibrates so that it is in the first position X, then moves to position Y, and then back to position X 50 times each second, which means this switch is flickering back and forth 50 times each second. Whatever the current that you're recording over here is a total coulomb per second, the total amount of charge that is passing over 1 second. But within this 1 second, this capacitor is charging and discharging 50 times. So whatever the amount of charge that this capacitor is sending through the ammeter in a 1 second duration of time, it is charging and discharging 50 times within this 1 second duration, right?
Yes, sir.
So each charging process should accommodate 1/50th of the total charge.
Oh, now I get it, sir. I couldn't grasp this idea at the first try.
No big deal, no big deal. Then the capacitance of the capacitor, that's pretty simple, I think. Q equals to CV gives you this capacitance. এটা তো পারবা, you get the Q from here.
Yes, sir. এটা পেরেছি।
ঠিক আছে, beautiful. মানে এই চার্জটা পারলে এটা ইজিলি পারা যাবে. This is a sequential problem. And there should be an ECF for this question answer as well. Have a look at number C. The question number C says a second capacitor having a capacitance equal to that of capacitor C. A second capacitor having a capacitance equal to that of capacitor C is now placed in series with C. Okay, so we now have two capacitors, which means now our capacitance has decreased, right? Series with capacitance now increased. Capacitance has increased now. Series decreased. Sorry, decreased. Such explains the effect on the current recorded on the ammeter. Okay, so if we have two capacitors over here, the total capacitance would be what? Half of a single capacitor. ठीक ना?
Yes, sir.
So if the total capacitance is half, which means the charge stored within for the same voltage supply would also become half. If the charge stored becomes half, it means drain charge would also become half, which basically means the total current recorded in the ammeter should simply become half, because the total capacitance have now become half. So the new recorded current should be 2.25 microampere. That's my best guess. This is two market questions over here. So the way we're going to write is that counting an identical capacitor in series causes the combination to have half the capacitance compared to the single capacitor. Half capacitance stores half the charge for the same voltage supply. So the current value becomes half because it now drains through half the charge. That's what I think, but I'm going to look at the mark scheme anyway. 7. Here is 7. Total capacitance is half, current is half. Yeah, basically it. Anything else, anyone?
Sir, could you repeat why current is half when total capacitance is half?
Sure, I can write. You understand why the capacitance would be half. It is the ucho. I mean,
Yes, sir.
okay.
They're both in series.
Sure. The equation is Q equals to CV. Your voltage source remaining the same, 120 volts. So voltage source is no change. So whenever the capacitance becomes C by 2, essentially the Q should also become Q by 2 for the same voltage source.
Okay, sir.
So whatever the amount of charge that you are storing within the capacitor earlier, now we are gonna simply be able to store half the charge. Half the charge, because Q equals to IT. If your Q becomes half, your I should also become half, because you're basically draining half the amount of charge per second compared to earlier, because you are storing half the charge compared to earlier. So simply current also becomes half.
Sir, I got a few questions from Compilation 5, electromagnetism.
Sure, we can go there. Mugdhu eta bujha geche to purapuri. We're moving on.
Yes, sir. Thank you, sir.
No problem. Compilation 5, the electromagnetism compilation. Yes, we'll pick that up. Sorry, compilation 5 in booklet 2. Electromagnetism is. Okay, bolo কত number?
Sir, question 3B at first.
3B. Okay. An early line code transformer is just in 6.1. We have the input, we have the output. This is a step up transformer. Secondary coil has more turns. Reason why the supply to the primary coil must be an alternating current, not direct current. Okay. For constant input power, the current output current must decrease if the output voltage increases because of energy conservation law. You have to state that and eventually use it. Okay. And then it says B. On phase to show the variation of the T of the current of IP of the primary coil. There is no current in the secondary coil. So complete figure sequentially to show the variation time of the magnetic flux on the core. Complete instance to show the variation T of the EMF induced in the secondary coil. Hence state that the phase difference of the phase difference will be 90 degree. Let me show you. Okay, I have to select this. So the first thing you have to understand that the primary coil basically creates the magnetic flux. The magnetic flux phi, which is given by BA, this B is created from the primary coil. So, and phi is also created from the B as well, which means the shape of IP, the shape of magnetic flux, and the shape of phi, all of these things would be identical with respect to time. Their graph shapes would be identical, which means shapes would be identical, but definitely we can have different axis values over here, so that their size can be different, but their shape should be identical. They should be in perfect phase. However, if you consider the EMF generated on the secondary coil, so I'm going to write EMF secondary coil, that is given by minus d phi by dt. So to get the graph of the induced EMF on the secondary coil, we have to get the differentiated graph, the differentiated graph of the primary coil, and then again we have to make it reverse, minus. So what you can see over here, that for the primary coil we have a sine curve, so the phi would also be the same shape phi curve, sine curve. So just make a sine curve over here as best as you can, and the EMF would be the negative of this thing. So your EMF graph would be minus d sine graph, d by d theta of sine theta. So sine theta ke differentiation করলে আসে cos curve, minus cos curve করলে যেটা হয়, minus cos curve মানে হচ্ছে it will start from the -1 and then you just continue the minus cos curve. So this is how this graph is going to look like, something like this. If you are asked for the phase difference, you can simply say the phase difference is 90 degree, or you can say the phase difference is 270 degree, because you have the
Make a difference, right? So
you have the crest over here, and then again in this graph you have the crest over here. So the gap is 90 degree, or you can say for the longer side it's 270 degree. Either way it can work. I guess কি also বুঝি নাই আমি।
sorry, there's not much of a difference between 270 and 90, so same thing, right?
Yeah. Either of them should be correct. But what is the probability that the examiners appreciate? That's also another big deal. If you want to score good marks, so you might as well look at the marks that what the examiners want to see. Number 3, they say half radian or 90 degree. Oh, they stuck to 90 degree. It was common to find this question was not attempted. Of those who did give an answer, the majority failed to state a unit for the angle. Why? Anyway, so বুঝা গেছে কিনা?
Sir, এটা বোঝা গেছে, কিন্তু যদি আমরা মাইনাস সাইন না কাউন্ট করে আঁকি লাস্ট ইএমএফ এর জন্য, তখন কত মার্কস কাটবে?
মানে এই মাইনাসটা যদি না দাও,
জি
মানে
স্যার।
এখানে যদি শুধু একটা কস কার্ভ আঁকতাম তাহলে কি হতো? That's your question.
Yes sir.
We should be fine. We are far find this about. Same epigraph, same frequency, correct phase, to figure the same frequency. So you're gonna get one. You're gonna get the same frequency mark, but you're not gonna get the correct phase mark.
But phase wise I'm still correct, sir, right?
For this question, you might actually get away with it because the mark scheme is not very precise about where the crest should be. Because if this was a proper mark scheme, hear me out, this should mention that 90 degree phase shift with the first curve, with the graph starting at negative amplitude. They would have specified this. But since this mark scheme only says the correct phase with respect to figure 6.3, they are basically not taking into account the minus sign. So if you, for this question, if you did draw only cost curve, you might actually get away with scoring this mark. Although it was not entirely correct, but you would get this mark for this mark scheme.
Yes. So my next question is for C.
We'll go for that. Okay, we have for two long straight current where conductors PQ and X are held in a constant distance apart as shown in 6.1. The conductors each carry the same magnetic current in the same direction. Then from the above conductors are shown in figure 6.2. Current out of paper dot, current out of paper dot. On figure 6.2, draw arrows on which space for the direction of the magnetic field Q at into the current the XY level is arrow B. On 6.2, arrow draw arrows 1 in each case. Show the direction of the magnetic field at Q Okay, this is your question was for B.
For C, sir.
Acha, state universal law of action. Acha, see the manifest density at B at a distance d from a long state where carrying current I is given by this much. This is explained to why under normal circumstances where carrying the alternating current are not seen to vibrate. Make reasonable estimates of the magnitude of the quantities involved. Okay, this question is about that if we have two parallel wires carrying AC across them and the current is continuously shifting direction, why don't we see those wires practically to vibrate? Because if there is an AC, it means there is a gradual increase of current to maximum, then gradual decrease, then opposite maximum, and then zero, and so on and so forth. So there should be a variation of force. Variation of force should result in some sort of strong repulsion and weak repulsion, strong repulsion, weak repulsion. So there should be some sort of vibration seen across the two wires. But in physical case, we don't actually see it for values like this. The question says that make reasonable uses expression to explain why, under normal circumstances, wires carrying alternating current are not seen to vibrate. Make reasonable estimate of the magnitudes of the quantities involved. So here, to make reasonable estimate, you have to make reasonable estimate for the current I and also the reasonable estimate that of the value D. I is the current flowing through either of the wire. D is the distance between them. Now, let me show you a picture so that you can have some idea for what this reasonable estimate actually could mean. Okay, let's say this is a cable. This is a three-phase cable, although this has some coaxial property on the outside. Let's say this is a basic three-phase cable. This is a three-phase cable, but consider that one is ground. So let's say consider two of them to be, one of them to be live, the other one is neutral. Beautiful. How far inside this cable would two of these core would be apart from each other? These two wires, what would be the distance between the center of this wire to the center of the other wire inside this cable? What do you think? For a regular cable, regular AC cable or electric iron cable or washing machine cable, how far can that gap be? How big that gap is?
Not more than a few millimeters, sir.
So give me an idea for a few millimeters. How much do you understand by not a few?
Like 3 to 5 maximum.
Beautiful. So let's say 5 millimeters max. 5 millimeters is actually pretty big. 3 would be a much more reasonable estimate. So let's say 3 millimeters. Okay, that's one value. Good job. And then try to think of a typical value of amperage that a certain of this cable would carry for a regular use equipment. Regular use equipment can include for low power equipment you can consider bulbs. For high power usage you can consider AC. So I can help you in this aspect that try to think of a typical value for the power of these components. Typical power, you should have an idea, and divide that by 220. That's the typical voltage that we have, RMS voltage that we have in our supply. So if you divide the power by the voltage, you should get the RMS current. So guess what could be the maximum current that you can get?
So I cheated a little and looked at my AC adapter on my laptop, and I saw 2.318 amperes.
So 2.318 ampere. So let's say about 2.5 ampere. Because if you think for 2.5, let's say if your AC is a 1 kilowatt AC for a 1 or 1.5 ton AC, that they're usually 1 kilowatt. So if you divide 1 kilowatt by 220, so 1000 divided by 220, that gives you about 4.5 ampere. So that's the RMS value. So we can consider up to a maximum of 5 ampere is pretty common for a maximum ampere that we might have to deal with for a regular house experience. So 5 ampere works. It shouldn't be more than 5 for practical purposes, because other components works at operates at a much low power. So first you mention these two values. So in your answer for this question, you're going to write that one of the value is, let's say, let I equals to 5 ampere and D equals to 3 millimeters. For these two values, even if whenever you will place this value with their in SI units, because this multiplier in front of this thing, this is extremely small, 2 into 10 to the minus 7. For practical values of these two numbers, the total product of this whole quantity is going to be pretty small. So the magnetic field that one of these wire is going to be producing across the other wire for that distance and for that amount of current is going to be minuscule small. Because the magnetic field is very small, the force generated F equals to BIL, that will be also very small. Because the force is too small, it does not simply overcome the inertia of the whole object, and that's why we don't see it to be vibrate.
I understood, sir.
Have a look at the masking language. We'll have a look number 4. Such reasonable values of I and D. Mention of the expression F equals to BIL. Force between wires is small compared to the weight of the wire. So in this case, they have mentioned the other factor, weight of the wire, or I use the term inertia. We should stick to the term weight because that's what they prefer. So learn this now. In the examination report, you can see that a number of candidates did make reasonable estimates and then wanted to show that the force between the wires would be much less than the weight of one of the wires. However, most candidates scored very few marks. Most did not follow the instruction to make reasonable estimates, and consequently, they could not expect to be awarded much credit. Common misconceptions were that either the wires would vibrate too quickly for the vibrations to be seen, or the force would always be attractive so the wires could not vibrate. That's basically not the correct thing. So these are all the potential wrong answers. These are the correct response. I think that's pretty clear within itself.
Sir, this question reminded me of the AS estimate questions, like
Yes,
diameter,
yes.
etc.
It has a lineage to those things, apparently.
And
Yes,
so my final question is question 9.
we'll go for it. Other people, you can ask other questions as well. We have a lot of time to cover. Question number 9, Hall probe. Which one? All of it?
Specifically, sir, from 2 on, but because A1 I understand.
Okay.
So from
Go ahead.
A2.
A constant current is maintained in a long straight vertical wire. A Hall probe is positioned at distance R from the center of the wire as shown in figure 5.1. So we have constant current over here. So we're going to have magnetic field over here. The magnetic field over here should be going into the page by right hand grip rule. And the Hall probe is currently placed perpendicular to the face of the magnetic field line. So we should record the maximum amount of, we should record the strongest, highest value of magnetic flux linkage. And then the question says that based on when the Hall probe is rotated about the horizontal axis XY, the Hall voltage varies between the maximum positive value and the minimum negative value. That's because of the cutting. When the Hall probe is as shown in the figure, it is having the maximum cutting of the field lines when it is rotated by 90 degree along the line XY. About the line XY, not along, about the line XY, then it would cut 0 magnetic field lines, so it would be minimum / 0 and vice versa. Then the question says the maximum Hall voltage VH measured at different distances. The data for VH and corresponding values of R is shown in figures 5.2. So if we move this Hall probe along this line and vary the distance, so at different distances, we get different Hall voltage values. Beautiful. It is thought that the VH and R are related by the expression in the form of VH equals to K by R, where K is a constant. Without drawing a graph, use data from figure 5.2 suggest whether the expression is valid. Okay. Whenever you are asked to calculate a relationship like this without drawing a graph, the first thing you do is that you try to validate this relationship with at least 3 sets of data. Sometimes the masking might say 2, but I've seen in most cases 3 is good enough. You don't have to go for 4, but if you want to go for 4, you can go for 4. So here it says that VH by equals to K by R. So if you make it into linear relation, you're going to get VH into R equals to K. So the product of Hall voltage into distance should give you a constant number. That constant number might not be a perfect constant because we always have to consider the experimental mistakes, random errors of an experiment. But if they are within a certain closeness to each other, then we might say that this relationship is valid. But if they are pretty far away from each other, then we should say their experiment is not valid. So it has to be, it comes down to a point of your understanding of random error affecting the results of an experiment. So that's also something that you should have in your mind, because you could have done your experiments regarding random errors in your AS level in paper 3. So you take multiple values from here. You could do the first 3, you could do the first one, the middle one, and the last one. You could choose any 3 values over here and just multiply them and see if you get a single value that is close to 1. So if you do any of these things, you're gonna get around 0.3. I think this equation gives you pretty close to that. For example, I can see over here 0.290 into 1 gives you 0.29. And this gives you about something close to 0.29, 1.5. This gives you 0.28, 0.28. This gives you 0.2, 9, 7, or something like that. For at least 3 of the values, if you choose and do the multiplication, you're going to get numbers which are pretty close. And then you can say, yes, the relationship is valid. Which you will say.
Yes, sir. So just like compare like 3 values of k.
Exactly. You can go more than 3, but at least 3 is good. A graph showing the variation with 1 by r VH is plotted. State the features of the graph that is such that suggests that the expression is valid. That's pretty simple. If this relationship is valid, then VH plus 1 by r should be a straight line that passes through the origin. So you write the whole thing. It should be a straight line that passes through the origin. B number says the Hall probe in A is now replaced with a small coil of wire connected to a sensitive voltmeter. Okay, beautiful. The coil is now arranged so that the plane is normal to the magnetic field of the wire. State Faraday's law of electromagnetic induction and hence explain why the voltmeter indicates 0 reading. Okay, the Hall probe is now replaced with a small coil of wire connected to a sensitive voltmeter. The coil is arranged so that the plane, its plane is normal to the magnetic field of the wire. Okay, so what we are doing over here for this question is that in place of the Hall probe, we are bringing up a piece of coil. Might as well draw this. Let's say that is like this, and the place is come out, and the plane of the coil is perpendicular to the magnetic field lines, because in this case the magnetic field lines would be cross in this location. So giving some crosses to remind me of this information. So that's how we replace the coil. The question says that state Faraday's law of electromagnetic induction and hence explain why the voltmeter indicates a zero reading. So you just mentioned the Faraday's law of electromagnetic induction. That is, what is the law of Faraday's law of electromagnetic induction? That I think it is that the induced EMF within a coil is directly proportional to the rate of rate of change of flux linkage of that coil. এরকম না? I think so. কত নম্বর question এটা? 9B1. Rate of change of flux linkage. I'm sticking to that word. EMF is proportional to the rate of change of flux linkage. Yes, beautiful. That's the definition for the Faraday's law. And then it says that why the voltmeter indicates reading, because whenever we are keeping the wire in stationary form, in a stationary state in front of the wire, so you are just keeping it like that, there is no change of the magnetic flux linkage. Magnetic flux linkage can happen either if we bring the coil close or further, then there would be a change of B, or if we rotate the coil in its original place, then there will be a change of B because of the angle. But see, as long as we keep it in place stationary, there is no change of magnetic flux linkage, hence there is no EMF induced. So you just mentioned that. Then it says state 3 different ways in which an EMF will be induced in the coil. Well, I already said 2 different ways. We can move the coil closer to the wire or further from the wire, or we can move the coil along the line along the wire XY. That's one way. Or we can rotate the coil, or we can keep the coil in its position and make the current carrying wire carry an AC. If we don't keep a constant current in this wire, we can change this current into an AC, which will significantly change the magnetic flux linkage. So either of these, all of these 3 ways should be mentioned over here. Can you state and explain both? No, only state. So I'm going to write moving the coil along the line XY while keeping the plane perpendicular, while keeping the coil vertical, or I'm going to write keeping the coil in the same position but rotating it around the line XY, or using the XY line as an axis of rotation. I'm going to be a bit detailed about this because I want to score full marks. And number 3 is that changing the current carrying wire to carry an AC supply to carry alternating current.
So how about moving the wire itself?
Yeah, moving the wire will work. That's what I said in the first place, that moving the wire along the line XY gives you an EMF. Or if it's stationary, rotate, or you change this one. These are the 3 things that comes to my mind, but I'm going to look at the mark scheme. They say vary current in wire, switch current on or off, use AC current, rotate coil, move coil. Oh, they pretty much have covered the existing 3 points. Yeah, works. বুঝছো?
Yes, sir.
If you have a look at the examination paper for this B2, many answers lacked precision. For example, it was commonly stated that an EMF could be induced in the coil by moving it without indicating the necessary direction of the movement. That's pretty important. That's really important. You cannot induce any EMF if you move it in a circular pattern that would make the coil rotate around the current carrying wire in a circular pattern. That way you will not gonna produce any EMF. So moving only is not gonna do. That move must incorporate change of magnetic flux linkage. That's important. So movement should be precise. Then it further says that many candidates also decided to introduce into the answers extra pieces of apparatus such as magnets and solenoids. Such answers were outside the context of this question. Okay, yeah, makes sense. Anything else?
One last thing, sir, from 10A, like how am I supposed to draw the bridge rectifier?
Which one? 10.
10A.
Oh,
Just
drawing a bridge rectifier is actually really simple. The simple way to draw a bridge rectifier is that if you have a kite structure, can I draw a kite structure here? Yes, I can draw a kite structure here. Let's say you have a kite structure like this, and then let me just rub with the bigger size. So, tilting parts is here.
so you can use Control Plus to increase the size of your eraser.
Oh, I didn't know that. Thank you. Thank you. So let's say you have a kite structure like this, irrespective of the connection points. Well, obviously, supply has to come from two opposite sides, and the drain has to come from two opposite sides. You can always make a good bridge rectifier as long as you make the parallel sides having same direction. So you make the parallel sides having the same, aiming the same direction, and then the other two sides aiming the same opposite direction. This will always work.
The
Always.
polarity of the load is already given.
Polarity is already given. Where? The students have to the student is transfer the partial okay, yeah. Acha. So since the polarity of this thing is already given, so I might as well select this. Acha, what I showed you was if this polarity was not given, I mean that circuit would always work. But if the polarity is already given, then we might have to consider drawing it more accurately. So let's have a look. If this has to be positive, which means I'm just drawing some stuff over here. You don't have to write these positive things, but try to bear in your mind. Let's say this is the high voltage, and that high voltage should pass through here, which means over here we would definitely require this facing diode. That essentially dictates this one should be in this phase. That's the first thing. So this one comes in through here and then flows in through here. And then once again, we'll consider this one. Whenever this has to be a positive end, because this is an AC supply, this is a symbol for transformer. This part is a transformer. So if this is the high voltage, current should flow in through here. So which means this diode should be aimed in this manner so that the current high voltage current flows through, comes in here, and then eventually goes back. So, yep. So another short thing that you can remember that this positive end that you see should be the end point of two aiming diodes. That also works. Make sense?
Could you repeat that, sir?
The positive end of the load should be the aiming point of the two diodes for their closing end. I mean, you're gonna have two parallel. You're gonna have parallel sides having the same direction. So if you consider this drawing that I did for this one right here. So if you have a graph like this, if you have parallel sides aiming the same direction, there's always going to be one point where two diodes aim in the same direction, right? Like here, two diodes are not aiming the same direction, two diodes are not aiming the same direction, two diodes are aiming in the opposite direction. But there will be a certain corner where two diodes will always be aiming in the same direction. This will always be a plus side and the other one will always be a negative side. That's another way to remember. Or you can simply judge by the basic understanding. That might cost you a bit more time, but actually you can be sure of scoring the marks, which I think works better.
Okay, sir. Thank you, sir.
No problem. Other stuffs, people? If you guys don't give me problems, I'm gonna close the class. I'm gonna pause.